بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. In this video we will present a second design for the 4-bit tooth complement circuit. Here we do not use the truth table, instead we use a simple building block. We call it a 1-bit complement circuit. This circuit has only 2 inputs and 2 outputs, and it contains only 2 logic gates, OR gate and XOR gate. We use 4 copies of this circuit to build the whole circuit, which is the TwosComp2 circuit, where we feed each bit of the input into the Xi of each of these 1-bit modules. For each DO of this module, it is fed into the DI of the next module. The YIs here represent the final output of the 4-bit TwosComp2 circuit. Now let us see the Verilog modules for these 2 circuits. This is the Verilog module for the first circuit, which is the 1-bit comp. Here we have 2 inputs Xi DI, 2 outputs Yi DO, and we have 2 logic gates, the XOR gate and the OR gate. Here is the module of the TwosComp2 circuit, which is the whole circuit. We have an input of 4-bit long X and output is 4-bit long also Y. And here we have 4 calls to this module, where we feed one input of the X into each of these calls, and for each DO of this module it is fed into the DI of the next module. Now we want to simulate these circuits. We will use the model sim that is integrated into the Quartus Prime software. Let us go to the Quartus Prime software. Here we will start a new project, new Quartus Prime project. Then we will select the folder where we want to save our files. I will save it into my documents, and I have here an alternate folder where I keep all my projects. I need to name this folder, a folder for this project. We'll call it TwosComp2. Also, I need to give a name for the project. We'll call it also TwosComp2. Also, I need to define a top level design module. I will select here the 1-bit comp. Then I will say finished. Then it will generate the folder and the new project. Now I need to define the two modules, one for the module of the circuit and one for a test bench to test the circuit. I will start with the 1-bit comp circuit. So I will define first the 1-bit comp module. I will say here Verilog HDL. I will copy paste the module from here. Here the module. I need to save it. I will save it. I will use 1-bit comp name. Now we need to also to build a test bench module. I'll go also to new Verilog HDL. Okay. Also, I have this module here. We'll go and see this test bench module. This is the test bench for this circuit. I start with module, then a name for the module. Here I called it test 1-bit comp, then semicolon. Then I need to declare the inputs using the rec keyword and declare the outputs using the where keyword. Then I need to call this module that I want to test, which is 1-bit comp, and I call this instance OBC. I will give it the input XIDI and I will get the output YDO. Then I will make initial begin end, and between initial begin end I will put all my scenarios. Since I have only 2 inputs, I have only 4 scenarios, 0 0 0 1 1 0 1 1, and after each scenario I wait for some time units. Here I use 10 time units. Then end module. Let me now copy this module to here. Now I need to save it. I'll use this name. I will copy this name to use it for this module. I will say save. I will give it this name, 1-bit test 1-bit comp, then save. Now I need to do analysis and synthesis to check for syntax errors. Zero errors, so I can go now to tools, run simulation tool, RTL simulation. Okay. This will start the model sim simulator. So this is the model sim simulator. Here I go to the work. Now this is the module I want to test. I can go now to compile. I go and select now the test bench module, which is this one bitcom. Double click. Now it says 0 error 0 warning. Then I say done. Now it generated a module here called test one bitcom. Double click. Now I select all these signals and I drag and drop them here in the wave window. Here I can change the type of the output to binary, and then I can go to simulate, run all. This is now the final simulation. I can zoom in and out to see the results. Let us zoom in. Let us start with the first scenario. This is the first scenario where we have inputs are 0 0, xi di are 0 0, and as we know that the yi represent the XOR and the DO represent the OR. So the yi is XOR. So this is XOR and this is OR. So since we have two zeros, so we'll have for the XOR 0 and the OR 0. Also the same here. We have 0 1, so the XOR will give us 1 and the OR will give 1 also. 1 0, still the XOR will give me 1 and the OR 1. For 1 1, the XOR will give me 0 and the OR will give me 1. So it seems that my design is correct. Now we'll repeat the same process for the full circuit, which is the 4-bit TwosComp2. Let me close this now. Are you sure? Yes. I'll go now back to the Quartus Prime. Now I'll create a new module for the TwosComp circle. Say new Verilog HDL. Okay. And now I'll copy paste the TwosComp module. Also I'll save it with the same name, TwosComp2. Say save. I'll give it the same name. Save. Now also I make another module for the test bench. And I will show you this bench here. This is this bench for TwosComp. Here we will name the module test TwosComp2, then semicolon. As I said, we need to declare the input as reg and the output as wire. So we have reg T20X, wire T20Y. Then we will call the TwosComp module 2, and we call the instance TCMB1, for example. Then we'll give it X and it will give us a Y, the Y output. Then initial begin. Here, since we have so many scenarios, we have 4-bit inputs, so you have 16 scenarios. We can use a loop. So we will start X by 0, then we wait 10 time units, then we repeat 15 times, and each loop, each iteration, we change the X by 1. So we add 1 to the X. So we start now X equals 0. Then that first iteration will add X to 1 to become 1. Then we will wait 10 time units and so on. This will generate the 16 cases from 0 to 15. Let us now copy this. And go here and save it. I will save by the name TwosComp2 or test TwosComp2. Save. Also now I'll do analysis and synthesis, but before that I need to change the top level design module. Instead of 1-bit, I'll say settings. Then in general I will call it here TwosBitCom. TwosBitCom2, I think COM2, yes. TwosBitCom2, this is the same name here. Not this name, the module itself. TwosComp2, not TwosBit. TwosComp2. TwosComp2, this is the name. TwosComp2. So apply, okay. Now I can do analysis and synthesis. Double click to check for syntax errors. We have 0 errors. We can now go to tools, run simulation tools, then RTL simulation. This will start the model sim simulator. I can check here and work. Now I have these two modules, the TwosComp2 and TwosComp2 calls the one bit comp. So these are both integrated together. Now I can go to compile, and I select now the test bench in TwosComp2, which is test TwosComp2. Double click. I have 0 error, 0 warnings. Done. Now I go to the TwosComp2, double click here. Now I can drag and drop these signals into the wave window. Now I'm ready now to show or to run the simulation, but before I do that, I will change the type. I'll keep it binary. I think I will need to change it to binary. Let me check they are binary. Go to Radix and say binary. Now I'll go to simulate, run all. And this is now the result. I can now zoom in and zoom out. So I can now check the results. Let me start from the beginning. See here in this first period, we have this is the X and this is the output Y. So the TwosComp of all zeros, it is all zeros. The TwosComp of 0, 0, 0, 1, we keep the first non-zero, then we flip all the others. So the TwosComp is correct. Let me take another example. Let me take this example here now. We have this is the input 1, 0, 0, 1. So the first one is kept as is. Then we flip the others, so it's correct. Let me take also one more different example. Let me take this example. Here we have 1, 0, 1, 0. So all leading 0 is kept as is. The first non-zero is also kept as is. Then we flip the others. So it seems that my design is correct. And thank you for watching this video. See you for